Hi, this is Professor Fernandez, and this is video 1 in lesson 17. So this video's purpose is just to get you comfortable with the notation for the definite integral. We'll do that across two examples from Calculus Simplified. So let's see what they say. First example up here says express the area of the shaded region in this figure as a definite integral. So I'm just going to remind you really quickly for the notation of a definite integral. So that's integral from a to b of f of x dx. F of x here is called the integrand. It is the function that you are given that is graphed between the interval a to b on the x-axis. So first thing we'll have to do over here, as you can see, is find the equation of this graph. And we can see already that the interval that the shaded region generates or is contained within is x equals 0 to x equals t. So already we can start to write out a little bit of the definite integral, 0 to t. We still need that function, and then there's a dx. You might be wondering, what does dx mean, and why is there a funny symbol here? Long story short, the definite integral is a sum. This is kind of one way that this integral symbol originated, is a sum of areas. Specifically areas of rectangles, where the height of the rectangle is f of x at location x on the x-axis, and the width is dx, right? So draw your quick little graph here. Let's suppose I go from a to b, and this is my function, y equals f of x. If I draw a tiny little rectangle here of width dx, there we go, and I go up to the function, if you imagine dx being super, super tiny, then I can approximate the area of this rectangle by the y value of the function, f of x. Or I should say approximate the area of this rectangle using the y value of the function as the height of the rectangle. So the area here is f of x dx. And then if I add all of those areas, that is what this sigma symbol means. And you can see that sigma is kind of like an S, and you can see this S kind of morphing over time into the integral symbol that we use for calculus to denote areas. So that's kind of a quick intuitive explanation of what the definite integral measures. And for our purposes here, we're going to go back to the example, and last little bit of information we need is that function. So I'm going to scroll or zoom in here to the right-hand side, try to figure out the equation of this function, and we can do that in a variety of ways. Probably the fastest one is to note here that it's a linear function, okay? So I want to find the slope of this function. How do I find the slope? Well, the slope is the change in y over the change in x. Notice that if x changes from 0 to t, so if delta x equals t, then y changes from 0 to 32t. So delta y is 32t. So 32t divided by t gives me just 32. Okay, I'm assuming t is not 0. I can do that because I'm just finding the slope. So my first guess at the equation for this line is 32x, now plus b. I'm using here y equals mx plus b form, and then I can go back and use a point to help me find b. I see that the graph crosses through the origin, which is 0, 0. So when y is 0, x is 0. That means that 0 plus b equals 0, so b is 0. Right? The y-intercept is the origin. Okay, so I get rid of this b, and this is the equation of my line. So I can put that up here. This is the line y equals 32x. This isn't the only way you could have found the equation of the line. There's a bunch of other ways you could do this, but I did want to try it this way so that I could get you to review simple things like how you find slopes, the y equals mx plus b form, and how you calculate b within that. All right, so now that we have the equation of the line, we're going to take that and plop it in here, 32x. So this is the definite integral that represents the shaded area over here. In terms of just notation, right? We are at this point in the course talking a little bit in chapter 5 about how to connect integrals to areas between the graph and the x-axis, like this one. This is the area of a triangle, so we could actually calculate this integral if we wanted to, right? Which is pretty cool, because at this point in the course we have learned nothing about how to calculate integrals of functions, except for in these very simple cases when we can use geometric formulas to help us out. So let's see this all over again for this example, which is slightly more complicated. At this point, I want to again figure out the equation for this graph. Once more, it's a line. And notice that as x ranges from 0 to t, in other words, the x changes from 0 to t, so that delta x is t. What happens to the y values? They start at 1 and they go to 1 plus 2t. That is delta y. Delta y is 1 plus 2t minus 1. So delta y is 2t. So delta y is 2t. So the slope is their ratio, which is 2. So I know the slope, and then as before, I write out my mx plus b form, and I find the y-intercept b value. So I know here that the graph crosses at x equals 0, y equals 1. That's this point right here. So when y is 1, x is 0, and that leaves me with b equals 1. So I go back here, I update the 1, and that gives me my equation of the line. So 2x plus 1 is the equation of this line. Great. So in terms of the definite integral, that tells me that the area of the shaded region, this one, right? I'm going to be integrating the function 2x plus 1 with respect to x, and I'm going to go between x equals 0 and x equals t. So 0 to t. And that is my area. Okay, so just zooming out here a little bit to do a very quick little recap of what we did. The definite integral is a very specific way to capture the area between the graph of a function and the x-axis. I want to be very careful there that thus far in the course, we have not talked about graphs that go below the x-axis, right? Like this one. We are going to talk about that concept called net signed area a little bit later in the course and in a later video. So, but for now, you can see that we're just concentrating on graphs that are either above the x-axis the whole time, like this one, or above and maybe touch the x-axis. And in that context, the definite integral measures the area between that graph and the x-axis. The notation, right, the a and the b value are the horizontal extent of the graph, right, 0 to t, 0 to t. And then you have the function itself, and then the dx goes back to what we mentioned earlier, that in this notation, this is really a shorthand for the sum of the areas of rectangles of height f of x with dx as we add all those little rectangles, right, to try to get the area below the graph, right, and between the x-axis. So this is my attempt here to show you how if I add up all these tiny little areas down here, I would approximate this area over here. Okay, so that's a little intuitive explanation of where the dx comes from and why it's there. Thanks for watching.